bottom, subject to modulation by various chemical factors. There are 3 chemical factors that come into play. Go back to this slide. And we have receptors for these 3 components or modifications of them. These are the 3 important factors that affect breathing: arterial PCO2, arterial pH, which means the number of hydrogen ions, and arterial PO2. Notice everything is arterial. So it's not what we have in venous blood, all right, that's coming back from the tissues, but it's the blood that's leaving the lungs. That is important. So I'm going to erase this board and redraw this section and then the blood supply where we have it. So if you want images of this, now would be the time.
So on the oxygen dissociation curve, did you say in there only the RV?
Yes. So we have 2 different locations for these chemoreceptors that are responsible for changing the rate and depth. And they are described as central chemoreceptors and peripheral chemoreceptors. So the central chemoreceptors are in the brainstem and they are within the medulla. So if I diagram this a little bit smaller, this again is CSF, okay? And our ventral chemoreceptors, our central chemoreceptors, they are in the medulla. And the peripheral chemoreceptors are in 2 sets of blood vessels. So we have the aortic arch, and off of the aortic arch we have the right common carotid and left common carotid, and then those give off the external carotids and internal carotids. Okay. In the aortic arch, we have chemoreceptors, and in the area where the carotid arteries branch, we have chemoreceptors. And so these are the central chemoreceptors. And these are the peripheral chemoreceptors. The receptors in the aortic arch will activate sensory neurons of the vagus nerve. Not the autonomic neurons. So we're not talking about parasympathetic motor, but sensory neurons within the nerve, hence the cell body outside the central nervous system. That would be the equivalent of the dorsal root ganglia. Okay. And peripheral chemoreceptors in the carotid sinus are going to activate sensory neurons of the glossopharyngeal nerve. Now we have different differences in the sensitivity and what is being detected by the central chemoreceptors and by the peripheral chemoreceptors. So central chemoreceptors are sensitive to arterial PCO2 via CSF pH. All right? So arterial PCO2 via CSF hydrogen ions. So as hydrogen ions build up in the CSF, they will bind to and cause changes in the central chemoreceptors. That is their primary component. They are not sensitive to arterial PO2. Okay? And they cannot detect arterial hydrogen ions. So they are not sensitive to arterial PO2 or to arterial hydrogen ions unless they become very, 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 very high in number. Will they actually even cross the blood-brain barrier? And if they do cross the blood-brain barrier, then bicarbonate ions are crossing as well and buffer them. So how does this work? You actually know the formula already. So this is representing the CSF. All right, so in the CSF, but I didn't draw this large enough to write everything in there. But in the CSF, we have the diffusion of carbon dioxide coming out of our blood vessels. So remember, we have pori plexus that the CSF fluid comes from, epidermal cells and capillaries. So from the blood, CO2 will diffuse into the CSF, and those cells also make carbonic anhydrase. And so we have that same formula, carbon dioxide plus water, and we have carbonic anhydrase. Ca stands for carbonic anhydrase. That makes carbonic acid, and that dissociates to form hydrogen ions and bicarbonate ions. So as those hydrogen ions build up, they bind to chemoreceptors. The chemoreceptors depolarize and release neurotransmitters, and those bind to the neurons of our dorsal respiratory group. So when I hold my breath, let's see how long I can. I didn't try it this morning. I'll be doing well with 38 seconds. I could have gotten to 32, but did you see the water level rising in my eyelids from those cartoons? Yeah. All right, so what was happening that drove me to take a breath? CO2 building up in my CSF, forming more carbonic acid, forming more hydrogen ions, causing my chemoreceptors to release neurotransmitters that activated my dorsal respiratory group neurons, which activated my phrenic nerve, which activated my muscle, diaphragm muscle, intercostal nerves, and my external intercostal muscles. Okay? So that drove that, okay, I have to take a breath kind of component. That's the central chemoreceptors, and that's primarily what we deal with every day.
That's why you can't
kill yourself by holding your breath.
Exactly. Unless you're in the pool and you hyperventilate first. Yes?
Can you explain the hydrogen ion effective, like what does that do exactly?
Okay, hydrogen ions, typically, let me draw a different cell. So back to our physiology with a nerve or any cell. So if I have a nerve, and we typically maintain our resting membrane potential through pumping out sodium ions and pumping back in potassium ions and the leaky potassium channels and all of that, all right? If I have hydrogen ions around this area, and I have more and more and more and more and more and more, what's that going to do
Concentration.
to the number of potassium ions that are leaking out? It's going to decrease because there's already positive ions there and the positive is going to repel more positive. So it's going to decrease the leaking out of potassium and the pumping out of sodium. So I'm going to start to build up positive ions inside my cell. That's going to cause voltage-gated channels that are dependent on the number of positive ions to open. So when the cell depolarizes, because of the increased number of positive ions in there, because they're not leaving because these ions are out here, that's going to open those voltage-gated channels, and that's going to cause that neuron to release neurotransmitters. And those will bind to other ligand-gated channels, and we instigate an action potential in other cells. Okay? So that's typically what changes our minute-to-minute respiratory rate. And the CO2 can be there because I'm holding my breath. The CO2 can be there because I'm exercising and breaking down more glucose to ATP. Or it can be there because of disease, as we'll see in our case study today. All right, so a variety of reasons that can increase the CO2. Again, primary, everyday, minute-to-minute change in respiratory rate and volume. Okay, our peripheral chemoreceptors. This is where we find the change in pH being determined and the arterial PO2. All right? So our peripheral receptors are going to be sensitive to hydrogen ion concentration. Now, why did hydrogen ion concentration not work here? We go back to the previous diagram. I kind of skipped over pointing that out to you. But if we go back to this previous diagram, see the bent arrow for hydrogen? That's because of the blood-brain barrier. The hydrogen ion, because of its charge and size, is not soluble in the lipid membrane of the cells and won't cross. Peripheral chemoreceptors are going to be dependent on the hydrogen ion concentration because they're in the blood already. There's no barrier to cross. So these are cells present in there already. And to the PO2 only if it is less than 60. This is arterial PO2. Remember, our venous arterial PO2 is, our venous PO2 is about 40. So we're talking arterial PO2. And PCO2 is not a factor. All right, so how do we pick this up? Here's an illustration of the carotid sinus and the group of cells. This would be the glossopharyngeal nerve here. And the group of cells that are sensitive to oxygen are called glomus cells. So here's a diagram of a glomus cell. And, see if I can put it over here. When the So when there is low oxygen, it causes, so a decrease in PO2 causes potassium channels to close.